Hey, greetings there, online biological science laboratories. Scholars, want to come to you with a brief overview of exercise 9, which you will not have to perform, okay? We have a little bit of a snafu because we had the first edition, second edition, so anyway, some problems, but you don't have to worry about that. All right, so exercise 9, the title is Diffusion and Osmosis, Passive Movement of Molecules. So if you hear passive movement, a corollary to that, must be what? Yeah, active movement. And active movement in biology, as you learned from the lecture, probably requires ATP. Passive movement is when you happy birthday to you and blow out the candles. You don't have to do anything to have the smoke to dissipate from the candles and just get dispersed. Or when you spray an air freshener on you, something like that. So things go from where there's a lot of it to where there's less, and it's just how it is on planet Earth. Now, on your book, page 85, it shows a little diagram there. See that? Under the intro. And it shows in figure A, all the little dots are gathered together. B, they're spread out, and C, they're spread out even further. That's how diffusion occurs, and it's due to a phenomenon called Brownian motion. And guess who peeped that and figured it out? Einstein. Yeah. So particles and small molecules and things like that, and molecules large too, they are constantly being bombarded, and as they do, it causes them to disperse. And there's this Brownian movement. So take a look at that. Okay. On that page 85, before we move on, at the top it has learning objectives, and that's what you should gather after having done this lab or studied about it. Recognizing hypertonic, isotonic, hypotonic solutions, predicting which way water will move. We'll get to that. On the next page 86, notice the bold terms. Okay, the bold terms are diffusion, and that's the dispersal of material from where there's a lot of it to where there's less. It's totally underplayed, but it's essential for the operation of your nerves, how you get oxygen into your body, and how material moves around inside of your body from fluid outside of the blood into the blood and there unto. It's diffusion, simple diffusion, but it's so profound because it keeps us alive. Also, as you remember from that diagram, A, B, and C on the previous page, it had a lot of it, a little bit less, a little bit more, more dispersed. So you can talk in terms of concentration gradient. For instance, if grandma is cooking cookies down in room 103, that's where the highest concentration of those good smells are going to be. But then if we have the door open, it'll come out and go down the hall, and it'll go turn the corner and go down there, but it'll be less concentrated. So what you can think of is a gradient from where there's the least to the most, or either most to the least. It's a gradient, and typically we represent it like with a slanted line. Okay, from high to low. Also on that page, it gets into what osmosis is and talks about a semi-permeable membrane. Semi-permeable membrane is a membrane that's will let some things through and others it won't. Okay, so that's what osmosis is, in the movement of water. All right, through a semi-permeable membrane. It gets down to materials which you're not going to use. All right, and I will post a couple of videos. And we get to predicting water, direction of water movement. So if you take a cell or a bag, a very thin cellophane bag, and put material in it and put water in it and put it in a beaker of water, what are the possibilities? Water could leave the bag, go into the bag, or go in and come out just at the same rate, so there'll be no change. And that leads to a discussion of what's called hyper, hypo, and isotonic solutions. And a special word is tonicity, that refers to the osmotic pressure that you have. Water is tending to either come out, go in, or it'll change equally. All right, so predicting the water movement. So it talks about hypertonic, hypotonic, iso. It's it's reverse logic of sorts. For instance, hyper means more. And if you have salt and water or sugar, you think more sugar, more salt, but it refers to where the water is. Let me back up. It means how much solute you have, solvent and solute. So a hypertonic solution is going to have more dissolved substance but it's going to have less water, and vice versa. All right. So let me just get a piece of paper and real quickly diagram this. Okay, here's an old cell. All right, and we're going to deal with salt and water, and that's an example in your book. There's 5% salt, and outside is 15% salt. And all we have is salt and water. There's my little diagram. Okay, if it's 15% salt, what's the other percentage that's out here in the environment around the cell? It's water, but what's the percentage? Yeah, you got it. Subtract 15 from 100, and it's 85% water. And then on the inside, notice I have 5% salt, and going towards 100, how much water do you have? 95% water. Okay, so looking at this situation, where is the greatest amount of dissolved substance, which is the salt? Is it inside or outside? It's outside because it's 15%, and inside is 5. So therefore, the solution around my little cell is hypertonic, and the one inside is hypotonic because it has less. So where is the greatest amount of water? In the cell, 95%. So therefore, water is going to tend to leave the cell. All right? And if the numbers were reversed, water would enter the cell, and that's a hypotonic solution. This is a hypertonic solution here, and it causes water to leave, and it could cause shrinkage. If it's hypotonic, it will be causing swelling, and if it's isotonic, then it'll be a no net movement. Put the top back on my thing. All right, on page 87, notice at the top it has a beaker and it shows some blood cells. You probably have to read it to know it. Now, if we were in the lab, I'd do this for you. And I just talked to my camera person, the person that shoots videos for me. She just came by my office today, and we're going to make some videos for you to help. All right, but I used to use my own blood. That's the point. I'd puncture my finger and put it in test tubes with hyper, hypo, and iso, just like you see these beakers. And what happens if you put my blood cells in hypo, water comes in and they swell and burst. Iso, no change, and hyper, they shrivel up, look like little potato chips, okay? And the greater the concentration gradient, that means I had 15 and 5 on my example here. If I had had 5 and 35, that would be a steeper gradient, and it would have a greater effect, okay? Now, in C on page 87, it says glucose versus starch. Glucose is a little molecule, and starch is a big humancho molecule, okay? And starch is made of glucose units. So there is my glucose, and this is starch. Now, this is not the scale. For instance, this guy right here should really be the size of one of those, or these should be the size of this one. But the thing is, it wouldn't fit on the page, okay? But the point is, this guy is small. It will be equal to just one of these, and this is a big conglomerate. So if you have a bag, a system with a semi-permeable membrane, the little guy will get out and the big guy will stay in, okay? And there are ways that you know from the last exercise how to test for starch and how to test for sugar. Use Benedict's for sugar and Lugol's iodine, or just iodine, to test for it. So if you take starch and iodine, put it in a bag, as shown here on the next page, 89, and put it in water, what will happen? Sugar will come out, but the starch won't. So you take sugar and starch, put it in the bag, put the bag in a beaker, make sure the bag is sealed, and the only way you can get out is going through the bag. And after a while, you'll be able to detect sugar outside of the bag, but you won't starch because it's too big. And how could you test the water to see if sugar's in it? Use Benedict's. And if you want to know if starch, use iodine. And what it'll do is it'll prove negative for starch and positive for it, okay? And again, you can play the game of the concentration gradient by having a lot of sugar or a little bit of sugar, you know, and that's how you can do it. All right. So the bag that you saw on the previous page, I'm not going to flip back. It can have holes in it of different sizes, and you can get molecules off of the shelf, and you know, of different sizes, and it can let you know what size the holes are, because whatever can get out is small enough to get out. So you just put in a bunch of molecules with different size, say like balls. You have a marble, ping pong ball and all that, and you have them in some kind of basket where there are holes or wire, and when they get too big, they can't get out. And when they're just right, they can come out, okay? So that's what that exercise will do. All right, there are some pre-lab questions and post-lab questions. And you just look at those using what I've said and what's in the book. What are the different types of passive and active transport? And it talks in terms of ATP that I know you've heard from lecture, okay? And it asks you to make a little diagram here. Again, look at this, but you don't have to submit anything for exercise 9. And what you would be answering is which way is the sugar moving. Now, the little bag that you saw with the bag with, I said, sugar and water and starch or whatever. Okay, what you do is take the bag, put the goodies in it, weigh it, and then put it in a beaker of pure water. And then take it out, weigh it again, weigh it again, weigh it again. If it's losing water, what is it going to get? That's right, lighter. And if it gets heavier, what is it doing? It's gaining water, okay? So a hypotonic solution causes swelling and a hypertonic causes it. And you could play the game with that and notice it would have you to check it out over time. 5 minutes, 10 minutes, 15 minutes. You do the weight, and it shows different salt concentrations. And the different salt concentrations would relate to the gradient, how steep it is. If it's a 10%, then, none. And if it's 5%, 2%, 1%. Very slow. All right, and then that's it. So that's it for exercise 9, and just look it over. You don't have to do it. This is a free spot, like in bingo. But osmosis and diffusion are essential for us. That's what your kidneys do. Kidneys control your fluid and electrolyte balance, and it's using the principle of diffusion and osmosis, okay? So diffusion and osmosis are very important for every aspect of what we do. So just wanted to come to you with that, and I'm going to say sign off here, and I hope this helps, all right? I'll put a quiz on for it, but use your book and, this video. All right, adios.